Welcome back. In this example that we're doing in this particular video, we're again looking at that whole idea of the product rule, but this time we'll be looking at non-independent events rather than independent events like our last video. So let's look at this example, okay, and we'll explain why this is a non-independent event. Okay, Mary Ann buys 5 tickets in a raffle in which 95 tickets are sold altogether. There are 2 prizes in the raffle, and it's asking what is the probability of her winning both first and second prizes, neither prize, or at least one of the prizes. Okay? Now, we're going to be using the product rule here in the first example, and the reason why is the whole idea of the word and. So, a bit of a hint to you when you're looking at probability problems, if you see the word or, you are generally going to be adding your probabilities together. If you see the word and, you're generally multiplying your probabilities together. So, let's look at this first example here. I'm going to explain to you why this is a non-independent event, okay? So this is going to be multi-stage, so she'll have her first draw and then she'll have her second draw, sorry. Okay, so it'll be multi-stage in regards to that fact. Now, let's just look at the probability of her winning a prize on the first draw, okay? So we'll call this W1. So the probability of winning the first prize on her first draw, well, she has 5 tickets. That means if she has to win one of those 5 tickets drawn out, okay, so she has 5 tickets out of a total of 95 tickets in the raffle, okay, so she's won on that first draw. Now, if you think about raffles, the tickets are not actually replaced, so the probability of her winning the second prize has actually changed. Now, let's think about this. If she's won the first prize, we can assume that one of her 5 tickets have been taken out, okay, so that now means that the probability of her winning the second one, well, she only has 4 chances of winning. Now, a common mistake that I see made by students here is that they put 95 on the bottom here, okay? But one of the tickets has been drawn out. It was her ticket, so therefore, she has 4 chances out of a total possible 94 chances in the second draw, okay? Now, it's asking us, what's the probability of her winning both first and second prizes? And the idea being, because it's n, we're going to multiply the 2 probabilities together. So the idea is the probability of win 1 and win 2 is equal to the probability of win 1 multiplied by win 2. Okay? You'll notice here it's just going to be 5 over 95 multiplied by 4 over 94. Okay? I'm just coming down the page. That's equal to 20 over 8,930, which is equal to 2 outside of 893. Sorry. Now, why are these events not independent? Remember that events A and B are independent if A occurring does not affect the probability of B occurring. So, if we look here, the probability of her winning in the first round affected the probability of her winning in the second round. Okay? So that is why these 2 events are non-independent. And it's a much similar process for how we actually find the probability of her winning both events, okay, in terms of the multiplication. But we just need to be careful about what the probability of each event occurring is based off of the previous stage of our problem, okay? So let's take a look at part B of this problem, the probability of her winning neither prize. So in this particular problem, let's think about it just in terms of the first draw, and then we'll think about the second one after, okay? So, for the first draw, the probability of her winning no prize, okay, that's the same as just the probability of not winning, okay, and I'm going to use this little notation here. That means the probability of not winning in the first draw, okay? Using complementary events, the probability of her winning was 5 out of 95, so the probability of her not winning is 1 minus 5 out of 95. So that leaves her with a chance, 90 chances of her not winning on the first draw. Okay? So remember, she has 5 tickets in, out of total possible 95, therefore 90 of those 95 tickets are not hers. Okay? Now let's just think about the second stage of this problem. I encourage you when you're doing non-independent problems to think about each step separately. Okay? So if we think about the second draw, so she hasn't won in the first draw, okay, so the probability of her not winning in the second draw, I'll use that same notation. So she hasn't won in the first draw. Let's think about how many chances that she still has left. 1 ticket's been drawn out, but it hasn't been hers, okay? So she still has 5 chances of actually winning, okay? 5 chances of actually winning because she hasn't lost one of her tickets. However, there are now only 94 tickets left in. So if we think of the probability of her winning in the second draw, she has 5 out of 94 chances. Therefore, the probability of her not winning, okay, the second prize in the second draw, is equal to 1 minus 5 out of 94, which leaves us with 89 out of 94 chances that she won't win in the second draw. Okay? So this is the probability of loss in the first round, 90 out of 95, and the probability of loss in the second round is 89 out of 94. Again, we can see that these events are not independent. Okay? The probabilities change depending on what happened in the first stage. Okay? So let's calculate the probability that she wins neither prize. Okay? So that's the same as the probability of a loss and a loss, using the same notation. Okay? Probability of not winning the first one, and the probability of not winning the second is equal to 90 over 95 multiplied by 89 out of 94. We know we're multiplying because of the word and, okay? And what that gives us, if we enter it into our calculator, is 8,010 over 8,930, which when we simplify this down, will just give us 801 over 893. Okay? Be very careful about what is happening in each of your stages of your probability experiment, okay? As some stages later on may be affected. Okay? So let's do part C. Now, in part C, it's asking us what's the probability that Maryam wins at least one of the prizes. Okay? And I want you to just think about this, right? The probability that she wins greater than or equal to one prize. Okay? I should put win in here. I want you to think about this. This is the complement of her winning no prizes. Okay, so just think about this for just a moment. The probability of at least one win is the same as not none wins. Okay, so just using that language there. Well, that basically means that we can have the probability of at least one win is equal to 1 minus, using that whole idea of a complementary events, the probability of 2 losses. Okay? Or the probability of 0 wins. So 0 wins here in this particular example. Well, we've actually found that in our last part, part B. 0 wins, where she lost both of the draws. So the probability of 1 win is equal to 1 minus the probability of no wins, or neither prize, which was from our last section, 801 over 893. Okay? So this gives us the probability of her winning at least one prize as 92 out of 893 total possible chances when she's trying to win this raffle. Okay? Alright? So, in this particular example, we didn't really use the product rule for part C. Okay? We used complementary events, but you can see how it related to the rest of the question. Okay? So, take your time when you're answering these sorts of questions. Think logically about the probability of each stage, and then put your answer together once you've done so. Okay? Remember, if you see the word and in a question, you're going to be multiplying the probabilities together. I hope this helps. Thank you very much.